The first section will introduce the background of reinforcement learning. The second section will conduct the detailed analysis of verl different concepts. The third section will cover some common use cases of verl, and the last section will bring some the latest news about verl. Firstly, let's start the first section. We will review the reinforcement learning algorithms in the field of large language models. The earliest method can be traced back to OpenAI's proximal policy optimization (PPO) algorithm. It is an actor-critic network. The actor first generates reward samples based on the prompt set, then calculates the reward scores and values of these samples, and finally optimize the parameters of the actor model and critic models according to the returns. As we can see, it actually forms a directed acyclic graph (DAG), which we can call it is data flow graph. The data flow graph is a core concept in verl because data is in various forms are flow into different models for computation. Then let's look at the Remax algorithm. It is a critic-free algorithm, so there is no training process for the critic model. Instead, it requires two reward processes to calculate two reward scores for the same prompt. In summary, we can find the data flow graph of reinforcement learning has three characteristics. Firstly, there are many models, including actor, critic, reference, and reward models. Secondly, there are many stages, usually including generation, preparing experience, and training. Thirdly, there are many workloads, including autoregressive generation, inference, and training. These characteristics undoubtedly pose great challenge to the training framework, making an out-of-the-box training framework particularly important. Above, we have made a basic abstraction of the reinforcement learning algorithm. However, in the implementation, we also need to consider how the hardware executes instructions. We can implement the computation on the cluster, like GPU clusters, in either in a parallel or non-parallel way. Parallel operations can be carried out simultaneously, but they require more GPU resources. Non-parallel operations cannot be executed in parallel, but they can use the same set of GPU resources. We also find that some computation have dependency. For example, most of computation rely on the initial autoregressive generation, and training always needs to be carried out at the end. Given this dependency, we need a well implementation according to the data flow graph. Then in the second section, we will introduce how verl specifically implements these data flow graphs. In high performance computing field, single program, multiple data (SPMD) is an important concept, which plays an irreplaceable role in today's large language model training. In SPMD mode, each process runs the same program, but uses different data. The distributed process that execute these tasks are called multi-controllers. However, the multi-controller is a low-level concept. Although it is efficient, the implementation is relatively complex. Therefore, a highly centralized single controller is also needed to implement the high-level training control logic. This is the hybrid controller programming paradigm of verl. It provides researchers with a good level of abstraction, enabling us to focus more on the algorithm side rather than on the engineering side. Under the programming model of single controller, the computation of reinforcement learning are replaced with some primitives, such as reward point compute reward and critical point update critical update actors and so on. And to to implement different RL algorithms, it only requires modifying just a few lines of code in the fit function. Yeah, the following is an example of replacing the PPO algorithm with the GRPO algorithm. We only need to remove the steps of computing values and use the advantage estimation of GRPO objective. Yeah, the flexibility enables verl to support a great number of algorithms, including PPO, GRPO, ReLU, Remax, Reinforced Plus Plus, Prime, Double, Doctor GRPO, and so on. Here is an illustration of hybrid controller programming paradigm. Taking the GRPO algorithm as an example, the single controller executes four different steps sequentially. First, it loads the prompts from dataset and use the actor model or policy model, we can call policy model to generate the corresponding responses. And then it uses the policy model and the reference model to compute the log likelihood, log props. Yeah. And finally, it uses the experience including the responses and log probabilities to update the policy model. This is the final step. Yeah, and therefore we can say the single controller breaks down the complex RL algorithm into very basic stages, which are not difficult to understand. Sorry. Another factor in reinforcement learning is that the execution patterns are different workloads are different. If the engines driving this workload are allocated to different devices, it will lead to a lot of bubbles. Because some operations generating auto generating takes a long time and computing the log likelihood requires a small a few time. Yeah. In order to improve the hardware utilization, verl has designed a hybrid engine. It is different from a hybrid controller. A hybrid engine it uses the same group of GPU resources to execute various computations and flexibly offloads the models by switching context to reduce the peak memory usage. For example, we can offload the policy model after generate sequence. After compute all the log probes and unload the reference model to compute the reference log props and then offload the reference model and unload the policy model for update. Yeah. So the hybrid engine is a multi-controller. It is deployed in the GPU resource pool and can be called by the single controller and the multi-controller. As shown in the following figure, the single controller sends the data from the driver process, single driver process, to the hybrid engine in the worker process for computation. This process is done by called the API of the worker group. Yeah, and the data partitioning of data parallel is completed simultaneously here. After waiting the worker to finish, the driver process then collects the results from the different multi-controller and for the next step. Yeah, next step. Fortunately, with the hybrid controller, verl supports leveraging different parallel strategies to maximize the hardware performance. Among them, the parallel strategies for training include the PyTorch FSDP, deep speed Ulysses for long sequence training, sequence parallel, and Megatron's 3D parallelism, including tensor parallelism and pipeline and sequence parallelism. Yeah. As for the parallel strategies during generation, tensor parallelism and expert parallelism of VLAM and SGLAM is also supported. Due to the design of hybrid controller, verl provides a feature to address the load imbalance in data parallelism, which is particularly crucial in long context training. verl improves the load balance through the following two features. Firstly, there is the balanced batch operation. This operation is to make the number of tokens in each data parallel rank more similar, more balanced by sorting the samples within each rank, within each batch. However, if gradient accumulation is enabled, this method does not work effectively. This is because each macro batch will trigger synchronization. Therefore, verl supports dynamic batching. This method can dynamically group samples into macro batches, making the size of macro batches more similar. In order to achieve faster training speed and lower peak memory usage, verl further supports the following optimization tricks, including padding-free training. It takes the advantage of the variable length input of flash attention to avoid computing padding tokens. Gradient checkpointing reduces the memory footprint of network activations through recomputation. Torch compare utilizes torch inductor for automatic kernel fusion and acceleration. And like a kernel is a high performance LLM kernel written in the Triton language. And LoRa is used to fine-tune model with low-rank adapters. In the second section, we described the main features of verl. In the following section, we will introduce the programming guide for using verl. In the first step of training, we need a well-defined data set. The data set should at least contain prompts. which are composed as a list of messages. The messages have a similar format with the OpenAI's API. It including a role like such as user, assistant, and a system, and a content including the text. Yeah. It also needs to include the data source. The data source is used to determine the reward function to be used. Finally, it needs to provide the necessary information for the reward model, such as ground truth answers to the questions. Yeah. For the reinforcement learning of vision language models, multimodal inputs like images and videos need to be provided. We recommend referring to our example Python scripts for data processing. It is provided in our GitHub repo. After the dataset is provided, we can define the reward function. verl supports using the function in an external Python script by configuring a custom reward function. The following is an example of its usage. We can input the pass to the external Python file containing the function definition and provide the name of the reward function, such as computer score. Yeah, the function name after definition. Yeah, and use the reward manager, such as naive reward manager and batch manager, and so on. Yeah, this is the example in YAML config and the example in command line config. The function defined in the Python script should be able to accept the parameters passed to the reward passed to it by the reward manager. It is an example of the naive reward manager. You can also refer to the naive reward manager has a core method, and it can receive the data from the actor model and other parameters. And we use the data, we use the solution responses and ground truth in the data to compute the reward score, and finally return the score to the single controller. Yeah, we have also designed some complex reward manager, like prime reward manager or double. It is equivalent to the reward in the paper. If you need to further modify the loss function, you can search for the location of backward in the code, and then modify the function of computer policy loss, or add other loss terms like entropy loss to customize the loss function in training. For example, the policy model, the updated policy method defines the loss function as follows. We compute the policy loss in same as PPO paper here. We can obtain the policy gradient loss, and then we compute the entropy loss. Then we can have the final loss by subtract the entropy loss from the policy gradient loss, and also K loss in GRPO, plus policy loss plus GRPO's K loss, with a coefficient of from config. And finally, we do backward here. Yeah. Under the design of hybrid controller, the training loop is mostly located in the fit function of the trainer class, retrainer class. We can modify the training loop by means of inheritance and overloading. Here is the example of the tuple algorithm. It mainly add some operations like filter groups. It filters the batch have extremely low and extremely high reward score, and use the batch with medium reward score in training. Yeah, it is the example. Yeah, in the last section, we will share the latest features of verl. We are currently, we are currently in the intensive testing phase of the reinforcement learning for DeepSeek V3 671 billion model. This feature is based on the GPT model implementation of Megatron and multi-node support of the inference engine, such as VLAM and SGLang, and the sharding manager for Megatron Core version 12 or higher. If you are interested, you can check out our PR 708. Meanwhile, we are also highly concerned about the reinforcement learning in multi-round conversations. For optimal performance, it requires asynchronous engine. Fortunately, the awesome SGLang team has integrated SGLang's asynchronous engine into verl. If you are interested, you can check our PR 1037. And Xibin Wu from our team has also implemented the asynchronous engine for VLAM V1. Thanks for his work. Yeah. Additionally, there are other updates, including adaptation to AMD hardware and SGLang support for vision language models and so on. You are welcome to pay more attention to the updates of our README file. Yeah. If you are interested in the materials of this presentation, you can scan the QR code on the right to obtain them for free. Yeah. That is all my sharing. Thanks you all.